So we're on 2A.3 exponential functions, okay? We started exploring exponential functions when we were looking at our sequence and series, correct? Exponential was used to model which type of sequence and series? Geometric. Exponential was used to model our geometric, okay? What we're going to do is we're going to explore a little bit more about exponential growth and talk about real world scenarios where we're talking about percent change per unit over time, because that's where it's used most commonly in real world, okay? First thing first is, what is an exponential function? Well, an exponential function is written as f of x equals a times b to the x, okay? Your b is a positive real number, okay? B is always greater than 0. That's what that means, right? B cannot equal 1, and your a cannot equal 0, okay? The domain of the set is all real numbers from left to right, negative infinity to positive infinity. Your b is what we call our growth factor, okay? That's our growth factor. And the just one should just be done today. And the constant a is the initial value. It's always, where do you start? It's your f of 0, okay? It's your initial value and where you begin. Got it? All right, so where we at? Next, characteristics of exponential functions. If a is greater than 0, which means a is positive, right? If a is greater than 0, a is positive, and b is greater than 1, then the exponential function will be an exponential growth. Your function is increasing from left to right. So we're going to draw a little sketch. It's going to be a little baby sketch right here. It's going like this. Please make the sound effect if you draw it. Otherwise, you're not going to remember what we did. There we go. Thank you for participating. I'm still laughing about that rooster. That turkey, whatever it was. I just thought when we thought about sign effects, I was like, what? I thought it was James, but then I looked and saw that James wasn't here. I was so quick to blame him. I was about to blame James. I'm like, James, what are you doing? And he wasn't even here. I was ready to blame him too, y'all. Next, if your b is between 0 and 1, that is going to be an exponential decay. So when we watched our geometric sequences, did we not notice that when we had that half, that 1/3, what were those values doing? They were decreasing, right? If we had anything greater than 1, they were increasing. So we're going to do it again. This time we're going from left to right. We are decreasing. Okay. That means it's a fraction of a whole, right? That means it's going to be a decreasing exponential decay, right? Which is what we should have taken away from our geometric series, right? All right, so we're going to start it with our parent function. What I want you to do, you should have a calculator on your table. I would like for you to create this function in your handy dandy calculator, and you're going to fill in the table, okay? Huh? So we're going to fill in the table. Who's going to get it? Rock, paper, scissors.
Good, always get your calculator. I mean, if I get up the right seat, okay.
All right.
Yeah.
So I want you to fill in the 2 to the x, and then we're going to talk about the relationship that takes place. So you're doing this part where it says 2 to the x. What does that give me? And then we're going to do the y together. Ready, set. All right. So here, 2 to the negative 2. What did we get? Can I write it as does it bother if I write it as a fraction? 1/4. And then what do we get? 1/2. And then what do we get? And then what do we get? Then and 8. Okay, so 2 to the x is our baseline. What happens if I want this for any y, right? Like, what if it's 3 to the x, 4 to the x? What would that look like? How is this going to affect? Well, there's a rule that's happening. Whatever your base is, so when we have y equals b to the x, there's going to be a rule that follows every single time. So it's just 1 over b to the b squared. 1 over b. 2 to the x was our... Because b stands for any base. Remember, we're using a variable, so that means it could be anything. Does that make sense?
1 over b.
So 1 over b squared, 1 over b. This is just going to be b. This is going to be, sorry, this is not going to be B. It's going to be 1. You saw nothing. Because anything to the 0 power is 1. So we have B, and we'll just have B squared, B to the 3rd. So that is the general rule for the parent function. Does that make sense? Okay, because our parent function is y equals b to the x, to model that, we typically use the 2, but from there, it can be anything, right? B can, yes.
Would it be negative or would it be positive?
Wait, so B equals 2 in this scenario?
Because it's the base of the exponential. Yes. It wouldn't be negative. There aren't any negatives because there's a horizontal asymptote that prevents us from going into the negatives, right? The negative y's. All right, so when we look at this, so this had been an example, y equals 4 to the 3rd, right? I mean, 4 to the x. If this had been 4 to the x, what would have been my negative 2? 1/16. What would have been my negative 1? 1/4. What would have been my 0? What would have been my 1? What would have been my 2? What would have been my 3? What's 16 times 4? 64. Yes. 16 times 4, 4 carry 2 is 64. Okay. So that's how you use the parent function. Okay. Following that rule, does that make sense?
Yeah.
The base changed, but the rules is going to be the same for every base. But because it's a variable in the base, we start with 2 to just model it. Okay. All right. So the domain of our parent function, the domain is going to be from negative infinity to positive infinity. Our range is going to be from 0 to positive infinity. So as x goes to infinity, so as x heads towards positive infinity, what are our y values doing? Going to positive infinity. As x heads towards negative infinity, what are our y values doing? Heading towards 0. They're trying to get small as they possibly can. Okay, and this is because we have an asymptote. What type of asymptote do we have? A horizontal asymptote. At y equals 0. That's because our values, no matter how small they get, they're going to keep reaching, trying to get smaller and smaller to 0. But can you ever have 0 in your denominator? No. So it's just going to keep, that's its goal, right? To get as close as possible to 0. Our intercept is always going to be at, we're going to have a y-intercept, and it's going to always be at the 0, 1. And in this situation, our concavity is concave up. Okay, so let's draw out our sketch. We have our asymptote. We have our 0, 1. We have our little 1/2, our 1/4. We have our 2, 4, and our 8. So I'm gonna now do my best to connect all these points. Be as concaved up as I possibly can.
Oh, yeah.
Okay, pretend that I touched 16 right there. Okay, it touched it. All right, how do we feel about the parent function? Everything starts here. Yes? Do we remember the parent function? We know it now. I'll take that. Forget the 4 weeks we learned about exponentials in Algebra 2. Totally. Exponentials and logs, what?
What's a log?
I'm going to ignore that. All right. So let's look at other versions of this. So here we go. It says here, we're going to, which of the following are exponential functions? Explain why or why not. Okay. So the first one, is this exponential? Yes, it is. Why is it? Because it's in the form, right? It's in the correct form. It's in the form of y equals a times b to the x. Okay, when we're asking what is its initial value, we're asking when x equals 0, what do we get? So when x equals 0, what do we get? 1. And what is the base of my exponential? B. And what is that here? 2. Yes. From whether it was a Thank you for remembering that. We did learn something about exponentials in algebra 2. Thank you. All right, so next here is B in exponential. Why is it not?
Yeah. That's what the case.
Wait, because the x is in the exponent.
You can't have a negative exponent. So this is no. And it's because of this guy. This guy makes this is actually a rational. This is a rational function. Okay. It's not exponential. It is a rational because this actually can be written as g of x equals 4 over x to the third. That -3 means that this variable actually belongs in the denominator. It's been a bad variable. It's because of the negative. Okay. The other way to check is its initial value. Okay. If my initial value of x equals 0 doesn't put me at 1, that tells you something. When I plug in 0 here, I get what? Well, I get no solution, right? Because if I plug in 0, what happens down here? It's gone. The initial value is undefined. Does that make sense? And my base here is x. And when you have an exponential, your base is a number, not x. Okay, what about this one? Is 5 times e to the negative x an exponential?
Is that an and or?
E is a number.
Oh, right.
And what's negative?
E is a number. That negative x right here, that's fine. My power is a number that's a negative. This is a negative variable.
So if it was a positive number, would it be okay?
Yes, if this is the problem is your x. Your x is not your power. Exponential means your x is your power. It's because of the x not being my power, and the fact that it's also negative makes it exponential. It makes it a rational.
For B, is that undefined?
For B is undefined. You're 0. That's because you have an asymptote, a vertical asymptote at 0. So you can't have an initial value, right?
Yeah.
Okay. Now, why is this? Yes, because E is a number and my variable is my power. Does that make sense? The variable X is the power. Okay, so the initial here. So if I plugged in 0, this would make this a 1. Does that make sense? I have something to multiply it to, which makes this turns into a 5. So this would be 1, but it has something that it has to multiply by.
Only 5.
What is my base?
5.
E.
Oh,
E is a number. E is 2 point something. Yes. Second, Ellen. You see it?
Letters or numbers?
It's been that for a while now. I don't know where you've been. In general. All right, is D an exponential?
Yeah. Wait.
No, it's just a number. This is not an exponential function. It's no, because this is a constant function. Why is it a constant? Because this is just a number. Okay. It's a constant function. And that's just because this is just a expression. You just plug that in. 3 times 4 to the E. That's a number. There's no variable. No variable.
Wait, so it's not a constant because what? There's
This
no-
is just a number. You know pi?
Yeah.
Pi is a number, right?
Yeah.
E is also a number like pi. Okay, it's another irrational situation. Okay, there's no variable as the power. It's not a variable. E is a number. If I type 3 times 4 to the E in my calculator, I'm going to get a value. Does that make sense?
So what is E? Like what is E?
E is 2.8 something. It's the natural log. We actually made a chart last year. Yeah, we made the chart last year for it.
2.718.
Yeah. All right, here we go. So in this case, our initial value, your initial value here is going to be
Wow.
what it is.
3.
So the base here is it's in terms of what we're looking at. Yes, we would think our initial value is 3, but there's nothing to plug in for 0, right? My initial value is gonna be the same as all of my values because this is a constant function. Does that make sense? It's a constant, so the value is gonna be 3 times E, 4 to the E, whatever that gives us. I'm just gonna write 4 to the E. If you want to write, if you want to write it out, I won't stop you. Our initial value is gonna be the same because it's a constant. It's a horizontal line. Does that make sense? If because you stopped it.
Oh, no, there is 2.7182818.
And the base width, is there a base?
Oh.
Mm-mm. It's NA, not applicable. It doesn't apply.